In the previous lessons, we talked about intermolecular force, basically the force created between molecules. And there are different types of intermolecular force with different level of strength. And intermolecular force is represented by IMF. So intermolecular forces. Well, in this case, if we compare the strength of different type of intermolecular force, we would have the strongest going to be ionic, followed by metallic. Then this is where the heart of intermolecular force is going to be. And it is going to be the types of covalent bonding. And there are different types of covalent bonding in a way that is forcing them to have different strength of intermolecular force. And the first one that we have is as a unique type of intermolecular force for covalent bonding is hydrogen bond. And hydrogen bonding intermolecular force is a specific type of dipole-dipole intermolecular force. And if you notice, hydrogen bond has its own unique name. That's because it is especially when we're working with hydrogen bonding with O, F, and then nitrogen. Okay, it's so unique to this particular 3 electronegative element. Now, of course, hydrogen bonding is stronger than dipole-dipole forces. And lastly, we have the weakest one of them all is the London dispersion. And this is also known as the van der Waals force. So this is the relative strength of different type of intermolecular force. Now, we did a lab called Chromatography lab. Today, we are looking at how do we analyze the data from the chromatography lab. So in a paper chromatography separation methods, a mixture like ink, like black ink, right, is made up of different visible components. Now we know black inks are made of multiple colors. And this visible component can be separated. And the way it works is that we're going to treat this mixture with a solvent. And that solvent will be absorbed by or travel up the paper by capillary action. So what is capillary action? Is an action where substance flow from one place to another place without assistance. And the distance that's traveled by the components, in this case we are going to look at one component at a time, is measured by the retention factor, which is represented by RF. So if we look at the formula for the RF, it's basically the distance traveled by the solute or the component that we're analyzing, and that is being compared to the distance traveled by the solvent. And if we have a paper chromatography like this, and this is our line, and this is where the dot start, it's gonna travel. So it traveled this far, right? But how is that possible with this? Because the solvent travel first, it's going to take along this component. And here you would have your solute distance, and here you would have your solvent distance. So this distance will always be higher than the solute. Now, why do we have different color of ink travel at different distance? Even when we use the same solvent, which in this case water. That is because the stronger the attraction between the solute and the solvent, the larger the RF is going to be. That means it's going to travel the farthest, okay? And if you have the weaker the attraction, the smaller the RF will be. So in this case, it would travel the shortest distance. And the attraction between the solute and the solvent can be predicted based on the solubility rules. And the solubility rule is basically saying that like dissolves likes. And this can be interpreted as like attract to like. What does it mean, like? Like is talking about the polarity, either non-polar or polar. So if we have a polar substance, that would dissolve a polar substance. And that's the reason salt is ionic compound, right? Which is NaCl. And that would dissolve in water. And water is a polar solvent. Okay? So keep that in mind, where nonpolar would dissolve in nonpolar. Now, if we interpret in terms of attraction, a polar solute would attract to a polar solvent. That means the more polar a solute is, it would have a greater attraction toward the polar solvent. That means it would travel the farthest. Compared to other substance or other component in the mixture that is less polar. So how do we determine the strength again? Remember, intermolecular forces. The stronger the attraction is, the more polarity is going to be. There, of course, where we have nonpolar solute, it would have a greater attraction toward nonpolar solvent. So the more nonpolar a solute will be, it will have a greater attraction toward the nonpolar solvent, which means it will travel farthest in a nonpolar solvent, which it wouldn't do here, right? By looking at the type of solvent, we can actually determine which component will travel the farthest or the shortest. And of course, this is compared to a less nonpolar molecules. And again, we use intermolecular forces. Let's look at an example. Here we have a polar solvent, okay? Think of this like H2O that we have in our lab. And this is how far it travels by solvent. And here, what can we tell about this particular component? Of course, if this is polar, this substance right here would be most polar out of all the three. What does that mean, most polar? It would have the strongest IMF. So basically, the stronger the IMF is going to be, the more polar it is going to be. Where down here, it travels the shortest distance, this would be the least polar. Or in terms of intermolecular force, it would have the weakest intermolecular force. And we abbreviate it by IMF. See how that works? Now let's look at an example where we have a nonpolar solvent. And of course, in this case, this is the travel distance by the solvent. And the solvent in this case is nonpolar. So if we look at this one here, this one would be most nonpolar. What does that mean, most nonpolar? That means this particular molecule would actually has the weakest intermolecular force. And we remember we have that list of intermolecular force up there, where down here would be least nonpolar. What does that mean? This one would have stronger IMF, which is intermolecular force. And that's the benefit of using paper chromatography. Not only that we can determine if a solution is a mixture consists of multiple components, but we can also determine the relative strength of their polarity or the relative strength of their intermolecular force of each component in the mixture. The limitation of paper chromatography is that it is limited to analyzing solution only, which is a homogeneous mixture in a liquid form.